This right here shows a standard hydrogen electrode. And again, what we have is a platinum electrode. Okay. And what was happening is because we have water present here, the hydrogen gas is flowing in, and then what happens is it's split then into the hydrogen ions. Okay, that's what's happening in this sort of a cell. And you can see that at the electrode atoms here, you've got the H2, and you can see how when it lands on there, the electron is taken up, and so only the hydrogen ion is left behind. And of course there's other counter ions so that you don't have too much of a charge right close to the surface there. So let's talk about standard potentials. The fact that you've got an E up here, okay, that means that it's a standard potential. The driving force of an electrochemical reaction is measured by the standard cell potential. It depends upon the nature of the redox reaction and the concentration of the species involved. So, the standard potential, where you've got that 0 up there, means all aqueous concentrations are at 1 mole. The pressure is 1 atmosphere or 1 bar. The temperature is held constant, usually at 25 degrees centigrade. Okay, when we are doing these, this right here is going to have to be measured in degrees Kelvin, and this would of course be 298 degrees Kelvin. And the units on this is in volts or millivolts. Okay, so the overall electric potential energy for a cell is what is the electric energy for the half reaction that occurs at the cathode minus the half reaction that occurs at the anode. So you're always splitting redox reactions into 2 half reactions. So here zinc is going to form zinc 2+, right? Zinc is being oxidized. Then a hydrogen is being reduced, right? And for this overall, this reaction minus this reaction for this one gives a net overall value of plus 0.762 volts. Plus means that that's the way it's going to happen. It's going to release that energy. For zinc, okay, this is just what we had on the prior one. This is a further explanation of that slide. So E0 for the half reaction cannot be measured. Okay, only for the entire reaction can you actually measure it. So the standard reduction is set, and then the value for the reduction has been assigned a value of 0 volts. This is the standard hydrogen electrode, SHE, okay? So it's against that value that all other values are then determined, okay? So what you're going to be doing is the measurement is always of this. But then we always base everything back to what occurs with this right here as a standard 0.00 volts. So zinc plus hydrogen going through zinc plus 2 and hydrogen is plus 762 volts. The energy of the half reactions has been assigned relative values. So this right here is the overall. You have that this right here, the redox reaction, what's the reduction of this going to this, okay, minus this one right here, okay. So the E of the anode is subtracted from E of the cathode because oxidation is the reverse of the reduction, okay. So this is how this one works, okay. So a cell permitting experimental measurements is the half reaction of, and this is, here again we have hydrogen as a standard, that's the standard, and here we have copper, and so we are able to measure this one right here, right? Because we know that this one is going to be 0. So these are values of the different half reactions. This is mercury 2. Now there is one mistake on this table in your I don't know if it's repeated in your book or not, but this has 3 plus. This should be 2 plus over here. Okay. If you add an electron when it's 3 plus, it becomes 2 plus. The other ones look the same. You'll notice that there are a couple of things where, because of the oxygen that's involved here in this species versus the OH that's here, you have to have the additional balancing of water and the hydroxide ion in that example. Likewise, that happens again when we get down to this equation right here as well. This equation, this ion has it, and also on the next page you'll see that in this one right and this one right here you also have where you have to take that into an account. Okay, so those are the half reactions for the different ones, and you have your values over here, and you can utilize those then to determine exactly what you're going to be having in each one. You'll notice that the standard where the crossover occurs is right here for the hydrogen one, which is 0. Now, let's go on then and talk about potential, free energy, and equilibrium. And this is going to explain the relationship between these 3 variables. So the calculated standard potential energy is positive, then the reaction is spontaneous. That's why the E of the cell for galvanic cells is always positive. If the standard potential for a redox reaction is negative, then it's non-spontaneous, it's not going to happen. You're going to have to feed current in and supply it. It's not going to supply itself. So the relationship between these. And if a spontaneous reaction occurs, we now know that the electropotential for that cell is positive. If that's happening, that we also remember from our prior work that the Gibbs free energy is negative and the K value, the equilibrium constant, is greater than 1. Okay? We'll talk about these equations as they relate to the variables. So first of all, the relationship between the potential energy and the Gibbs free energy is this relationship right here, where these zeros, as I said, indicate standard conditions. Gases at 1 atmosphere or 1 bar, aqueous species at 1 mole. This right here is the standard free energy change. I guess they're going to drop the Gibbs. Oops. This right here is the standard cell potential. N is the number of moles transferred in the balanced redox equation. Okay, so that's the balanced equation. That's what the N value is going to be. And F is called the Faraday constant. It's 9.648 times 10 to the 4th joules per mole per volt. Okay, and the key thing is noticing that this and the energy have the opposite signs, right? So that when this is negative, this is positive. When this is positive, this is negative. Okay? And that's relates to this, whether something is spontaneous or non-spontaneous in terms of those 2 variables. In redox equations, eventually you reach a state of equilibrium. So when that occurs, it's related to the equilibrium constant by this equation right here, RT divided by NF times the natural log of K. Okay, this is the natural log. Now, if you want to put the values in there that you can, at standard conditions, this is the temperature. This right here is the R value, and here's the Faraday constant, right? So all of those can be converted into this right here. So that prior equation can be converted to this divided by N times the natural log of K. And like I said, this only applies at 25 degrees Kelvin right here, right? Because that's what 25 degrees Kelvin would 298 degrees Kelvin, which is 25 degrees centigrade. And if E is positive, then K is greater than 1. If E is negative, then this is less than 1. So if you look at these equations, you can see that you have a relationship between the Gibbs free energy and the equilibrium constant, which we developed in an earlier chapter. And this chapter, what we learned is a relationship here between the the electric potential and the equilibrium constant, and the electric potential and the Gibbs free energy. Okay? 3 separate ways of looking at this. Now, to this point, we've dealt only with standard potential energies. Okay? Gases are 1 atmosphere or 1 bar, and the species are 1 molar. Since reaction conditions influence these 3 variables, the Gibbs free energy, the potential energy, this potential energy is also influenced by these conditions. Voltage will increase if the concentration of the reactant is increased and the concentration of the product is decreased. Voltage will decrease if the concentration is decreased or the reactant is decreased, the concentration of the product is increased. Okay? These are critical things to know about the effective concentration on potential. Likewise, you can also have temperature changes as well, right? And that involves the Nernst equation, where you have what it is for the standard conditions, as noted by the little 0 here, and then this natural log of where you are, since you're probably not at equilibrium, the concentrations of the various ones, and the Faraday constant. At 25 degrees centigrade, or 298 degrees Kelvin, this RTF, okay, and plus the fact that you have a natural log here and a regular log to the base 10 here, puts this sort of a factor into effect. Okay, so this is a second way of looking at that equation, and the key thing is to note that this constant at 298 only also results in a change from the natural log to the log to the base 10. Let's talk about some batteries and fuel cells. Okay, this is one of the earliest models of the fuel cell that occurred. We had zinc right here, with going from the zinc ions being formed at the zinc anode, and then copper becoming copper metal, the copper plus 2 ion becoming copper metal, where you have zinc sulfate as the one in solution here, and then the sulfate ion is the one that is flowing back and forth, and you have the flow of electrons in this direction. And this occurred way back in 1904 when they depicted this type of one, where they had a clay pot, so that the clay actually served as the salt bridge between the 2 half cells. This is the more current one. This is your 9-volt battery, which is made out of manganese oxide plus sodium chloride as a paste of that. You've got a carbon rod here. You've got a zinc can here. You've got a seal, an insulator, and then this right here is a typical dry cell. This one right here is an alkaline battery. These are the double A's and the little ones that you have, and you can see the different organization of the materials in here as compared to the other ones. You also have the nickel-cadmium battery, where you have essentially a whole series of different sheets. This is a jelly roll type of model. And then you also have the lithium-ion battery, where you have the lithium-oxygen metal with the graphite layers in there on the negative electrode, and this is a positive electrode, going back and forth for the charge and discharge of these rechargeable batteries. And I think that will be the end of it. This is your common lead battery.